Okay, so let's welcome back for the final session. So we have two talks. The first speaker is Anurag, who will tell us about quantum fields and maximal slide.
Okay, thank you. First of all, I'd like to thank the organizers for giving me a chance to speak here. So I'm going to talk about this work we put out recently with my wonderful collaborators Naveen and Spenta. So let's get started. So we considered two problems in black hole physics. The first one is about local diffeomorphism invariant operators in gravity. It's not specific to black holes. But what is specific to black holes is the second point. How does one describe the time evolution of infalling states? Means as something that falls into the horizon. Now, I will try to convince you that the key to addressing both these issues is correct gauge fixing. And after complete gauge fixings, there is a sense in which a probe scalar field becomes a local degree of freedom in semi-classical gravity. And the same gauge fixing will give us a foliation of the black holes whose slices probe the black hole interior and describe infalling states. Now, many of the things I'm going to talk about have generalizations to high dimensions, but in this talk, I'll mainly focus on the two-sided BTZ black hole setup. All right. So in case I don't make it to the end, let me just summarize the main results of our paper. So we work in the Hamiltonian formulation of GR.
I'm really sorry to interrupt
Sure.
you at this time.
Sure.
Because I'll forget.
Yeah.
Have you guys thought of double-sided JT? Because I think you can do what you're doing there also. Remind me later. We should chat.
Okay. Yeah, sure.
It's another concrete context.
I see. Thanks.
Field theory on space computation.
It will become it after gauge
They
fixing.
want to choose the gauge very carefully. That's very important for them. And there are similar issues, I think, which can be done very carefully in JT with matter.
Yeah, I'll you'll see. Yeah. So the Hamiltonian and momentum constraints are dealt with by fixing the maximal slicing gauge and the Dirac gauge respectively. So specializing to 2+1 with two asymptotically ADS boundaries, we show that the above gauge is fixed correctly without any residual gauge freedom. We then explicitly construct the smooth maximally sliced foliation of the two-sided BTZ black holes. The leaves of this foliation cut across the horizons, asymptote to the boundary time. They do not include the singularities, and the lapse always remains non-zero everywhere, including at the bifurcation surface. We then study the dynamics of a probe scalar field in the maximally sliced BTZ black hole. In the semi-classical expansion, working up to quadratic order in the scalar field and metric fluctuations, we will note that the scalar field does not mix with the metric fluctuations after gauge fixing. We write down the scalar field Hamiltonian, which propagates along these maximal slices in terms of a discrete set of mode functions of the scalar field that are smooth across the horizon. Now these modes mix both the boundary operators left and right and are appropriate linear combinations of the Hartle-Hawking modes. This Hamiltonian is a completely gauge invariant operator that lives in the product of the two CFTs associated to the two boundaries and describes time evolution of CFT states and operators. This is like a boundary description of what it means to be infalling. A final point is that our results are valid for evolution times much smaller than scrambling time, during which we trust that the BTZ black hole solution continues to be a valid saddle point of the gravity path integral. So I'll go ahead.
Do you have reason to believe it won't be a valid, at least saddle point, it will not dominate the...
It may not, oh sorry, yeah, that's the correct, yeah, you're right. It may not dominate the partition, yeah.
Just a question, when we do this, usually the kind of question we are trying to ask is, what is the correlation function of the the scalar field in the band, for instance?
Okay.
But that you can get even by taking the usual spot shell slicing inside and outside.
Mm-hmm.
So what is the advantage of quantizing the field in this particular sense? And what do we get that we couldn't get earlier?
When you do it that way, well, I'm not sure how gauge fixing enters there, which is something that's very important for us when we do this. See, I don't impose that my slices. I don't by hand impose that, let me work with these slices. I put a gauge condition that tells me which foliation to choose.
How it will enter there. It will
Yeah.
enter, when I want to compute a correlation function, I'll need to specify the point of which I can. And that point will be specified in a particular operational way. For instance, it might be that I shoot geodesics from the boundary, or it might be that I fix a gauge. But,
Okay.
But the point is, I can get all correlation functions just by quantizing the field in the Schwarzschild coordinate system, which is very easy to do. So, what I'm confused is, yeah. So the question is again, what is the result that we would get this way that we would not have, that we did not have earlier?
Well, what I have is very explicit expressions for everything. Now I agree that you can shoot geodesics and do things like that. I don't know how to do that very precisely and with analytic control. But what I'm going to do here will be under reasonable analytic control.
Let me suggest an answer and then
Yeah.
you tell whether it's right or you tell Sudha.
Yeah.
As part of your construction, won't you therefore be able to relate the bulk field to boundary operators on both sides in
Yes.
an explicit way?
Yes.
And in that way obtain a map of the bulk observable in terms of double-sided.
We know that.
Yes, yes.
We know that in the usual formulation, that boundary operators are a combination of left plus right. And in fact, gauge is important there. Depending on how you gauge fix, there will be slightly different combinations of left plus right. But we know how it depends on the gauge as well. In fact, I'll discuss a little bit. So it's a, like for if you fix gauge from the right, it's a particular combination. And if you fix gauge in some other way, it's a different combination. So that's gauge dependent. But that answer we know, right? That's the HKLL.
It doesn't, okay, you should say,
Yeah.
I thought when you have horizons and all, it's more tricky.
No, not in the if you're in a thermofield double state. If you're in a one-sided state,
No.
you'd be in trouble. But this is a thermofield
Yeah,
double.
he's doing
Then you do it from the left and the right, everything you get.
It's related to what you're saying. So I don't immediately know, have an answer why it's obviously better than what you suggested, but maybe we can come to it later.
The real question, like the interior,
Huh.
if you had only a one-sided CFT. If you have a two-sided CFT, obviously you get the interior. I mean, this is, I think, the thermofield double, for instance, is, if you have a
See.
thermofield double, you can construct, I mean, I'm not saying that this, the results might be nice in some way, but
Yes, yes.
since it makes it more, what some of you after is to construct when you have a single-sided one.
I think what we do here can be applied to single-sided black hole, but it'll be technically more challenging.
I think it's only technicality.
I haven't worked out the single-sided, so I cannot say. But it may be conceptually as well. Yeah, I don't know. I don't have a immediate good answer to that. Okay, I'll move ahead. So I'll talk about the gauge fixing conditions in a bit detail. Then I will put the BTC black hole in the maximally sliced gauge. And finally, I'll study the probe scalar field on this maximally sliced BTC black hole. Okay. So this is the familiar expression for the Hamiltonian of GR with a scalar field. N and Ni are the lapse and shift. There's a boundary term which I haven't written down here. H perp and Hi are the Hamiltonian and momentum constraints which generate space-time diffeomorphisms. So from the point of view of the Hamiltonian theory, they are first-class constraints and satisfy this following algebra. So we impose the maximal slicing gauge, which is just that the trace of pi ij is equal to 0. Now, one of the first things you do when you impose a gauge condition is you ask, calculate what its Poisson bracket is with the already present first-class constraints. So the spatial diffeomorphisms preserve the pi equal to 0 gauge, which just means that the Poisson bracket of pi with hi is weakly 0. However, the Poisson bracket with h per is this non-trivial object. So this is a differential operator. And I'll be working in asymptotically ADS spacetimes. Lambda is less than zero, and the scalar field, if the potential of the scalar field is negative, then this entire operator is negative definite. So the differential operator above has no zero modes corresponding to small diffeomorphisms, so which means you can invert it and define a Dirac bracket and so on. Now there are large diffeomorphisms which are zero modes. The laps is an example. It actually satisfies this acting on the laps equal to 0. So the invertibility of this operator tells you that there are no nearby solutions of h perp equal to 0. If you are sitting already, if you already satisfy h perp equal to 0, nearby there are no other solutions. That's basically the quality of a good gauge. But are there solutions finite distance away in the phase space? So basically I'm asking, can you fix this gauge globally in the phase space? And the answer to that question is yes, you can fix this gauge globally. To see that, you start with an arbitrary point, g prime and pi prime. I think this picture will be helpful. So here I've drawn the vertical guy is the pi equal to 0 subspace. The horizontal guy is the h perp equal to 0 subspace. So you start with some arbitrary point, which to begin with is in the pi equal to 0 subspace. Then while transform uniquely takes g prime and pi prime to another point g tilde and pi tilde, such that g tilde has a constant curvature equal to 2 lambda. After a further while transform, you can go to g and pi, gij, pi ij, such that it's on the h perp equal to 0 surface, but that happens only if the lambda here, which is the while parameter, satisfies this equation. This is the Lichnerovitz equation, and mathematical relativists have shown that the existence and uniqueness of solutions to the Lichnerovitz equation in asymptotically radial space times, and that guarantees that there is a unique point on the full while orbit. Right. So the final result is that you can always fix this gauge globally in the phase space. Once you do that, the intermittent degree of freedom is the while class of metric and traceless momenta. So it gets rid of 1 degree of freedom each from both. Now the Dirac gauge is given by the following condition. Now we are interested in momentum constraints. This is the Dirac gauge condition. It's while invariant, which means I can fix the gauge for any point on the while orbit. That's good enough. So now its Poisson bracket with the momentum constraints is a bit complicated, and in fact Dirac studied this long time ago and showed us that this operator on the right hand side is invertible in a small distance expansion. Now as far as I know, one cannot fix the Dirac gauge or any other gauge as far as momentum constraints are for momentum constraints globally in the phase space. So you have to work locally at in the neighborhood of a point in the phase space, and that's what I'm going to do. So I'm interested in the BTZ black hole. So I'm going to use a alternate method to do that. I'm going to use some results from hyperbolic geometry. The result is that a constant negative curvature metric on R times S1 can always be put in the following form. The reason I'm interested in R times S1 is because that's the spatial slice of my two-sided BTZ black hole. And one can check that this is satisfies or is already in the Dirac gauge. Now we come to perturbation theory, because eventually I will be working in perturbation theory. So this is our action root gr, but written in this Hamiltonian way.
So just to,
yeah.
In simple bracket terms, is it that you're fixing the spatial reparameterization freedom on each slice by choosing this geometry for the two-dimensional slice?
Yes, yes.
And then you're fixing your time reparameterizations in a sense by choosing some value for the overall Y factor.
Yes, yes. But they're a bit more detailed. So this metric G twiddle.
Besides this, I mean,
yeah.
The overall Y factor of the.
Yeah. The C to the 2 lambda, right? Yeah.
You're fixing that in a sense.
Yes.
Fixing which slice you are.
Is it maximal volume somewhere?
So that was right. So
the Y factor, right? That's how you fix the Y factor, right?
Yes.
Okay, so that fixes the Y.
Yeah.
And then the spatial reparameterizations you fix by choosing.
Right.
So Lichnerovitz equation, that was the equation for the Y factor.
Exactly. Yeah.
So you didn't write it in that form exactly, right?
This is that equation. So yeah. So R twiddle is twiddle means this space point.
So is phi the Weil factor?
No. So this at this point I'm working in general, more generally. So I have a scalar field. Eventually I'll work in perturbation theory, but the point is that this theorem is much more powerful. It allows for matter fields as long as they satisfy some form of strong energy condition.
Oh, sorry.
Yeah.
I'm just trying to get noted. D2 lambda is the Weil factor.
Lambda is the Weil factor. Yeah, that's right. Yeah. Sorry about that. Yeah. Right, exactly, yeah. So, I'm interested in the BTC black hole, right? Let's go there, right? So, at this point I said I cannot fix the gauge globally, so I work in the neighborhood of the BTC black hole, but I'm interested in a two-sided black hole, and the spatial slices would be wormholes, like the topology of the cylinder. So that's this R times S1. Is that clear? Okay, so let's come to perturbation theory. So what you do is you expand everything in this parameter kappa, which is square root g Newton. You expand every quantities you can think of and put it in the action and write down the action is in this perturbation expansion. So S hat is will not involve the scalar field, it will only be background. S1 will vanish because you're expanding around a solution of the Einstein's equations. S2, from S2, the quadratic piece, you can read off what is a Hamiltonian at this order. So this is the expression, this is the form of the expression you get for the Hamiltonian. And an interesting point here to note is that the scalar field actually does not mix with the metric fluctuations at this order, neither directly nor through the constraint. So this C perp and Ci are the Hamiltonian and momentum constraint at this order. Although I haven't written the exact expressions for you, they only involve the metric fluctuations and its conjugate.
Why is it surprising that you don't expect that there's a mixed term with the scalar field times metric fluctuation, right? But does this even depend on gauge? Like, I'm confused. Why?
No, at this point, this is separate. I will.
It's a quadratic statement right now, right?
Yes.
But why is it surprising that the quadratic level, the scalar field and the metric fluctuation don't mix if you're about a solution of the equation?
No, you would have thought that maybe they mix through the constraints. Obviously, if there were no constraints, then there's no surprise, because always at the quadratic level, all fields are independent.
No, it's more that you look at the equation of motion of the metric about
Yeah.
the solution.
Yeah.
And it has to be that the coupling is stress tensor of scalar field times the metric fluctuation. But the stress tensor of scalar field is quadratic in the scalar field. So if you're about a solution of the equations of motion,
Right.
don't you expect metric fluctuations? The first term can only be cubic metric fluctuation times two scalars.
Right.
You can't get, unless, because you're imposing the equations of motion.
Yes.
How could you get metric fluctuation times single scalar? It would suggest that the metric was sourced by a single scalar when you worked out the equation of motion.
Right. That's this part. I agree with you. I mean, maybe it was surprising for me, but it's not for you. I'm saying there was a possibility that they could have talked through constraints, which is the Gauss law at this order. But that doesn't happen. That's all I'm saying. Yeah. Maybe it's not surprising.
Gauss law will tell you that the metric is an integral of the square of the scalar field, not of the linear order of the scalar field.
Right. So at this order, it doesn't. Okay, that's all I'm saying. Okay. Yeah. Okay, we are on the same page. Yeah. All right. So the point is that once you fix the gauge completely, the scalar field is a local degree of freedom at this order. Now, if you were to go at the cubic order, then it's true the scalar field will talk to the metric fluctuations, but then I will further expand phi as some phi hat plus kappa phi 1. That phi 1 will again be local degree of freedom. That won't talk, that only talks to the background. So at any order in perturbation theory, you will have a remnant scalar field part which is local.
Are you saying that you're solving the equations of motion in perturbation theory and at every order you get differential operator times some metric and that's equal to source which comes from previous orders? Is this a statement of perturbation theory? Or?
I think so, yeah. All right. Okay, so once you fix the Dirac gauge and the maximal slicing gauge, you can solve for the constraints. From now on, we'll treat the matter in perturbation theory with the following boundary conditions, which are relevant for BTC black hole. To get this equation, so these are simply the become decoupled Laplace equations. You can solve them simply. Once you have this solution, you can plug it back to get this Weil factor lambda. So at this level, what you find is the reduced phase space, because all the independent data is just M and C, which determines everything, the metric and the Weil factor and everything, is just the reduced phase space at this level is just a pair of numbers M and C in the gravity sector and the scalar field which comes from perturbation theory. Right. So sorry. Oops. So when I wrote down this metric, M is like a modulus which controls the circumference at the center of my cylinder.
Is this just the asymptotic energy and angular momentum?
It gets related with that. Exactly. Yeah. That's why I wrote M. Yeah.
See a little bit more about the coordinates. So theta is like
Right, like a radial coordinate. So it goes from -π/2 to +π/2, and as you can see, this diverges. Phi is like the circle direction.
In higher dimensions, you would also have had the transverse trace in the physics.
Yeah. So yeah, exactly. Yeah.
You would still have had these angles.
I
Let's see a constrained degrees of freedom.
constrained degrees of freedom.
Then M and C are fixed by the scalar field. No? They're not. Isn't there a global constraint that relates M to this phi?
See, at this order, there's no scalar field, right?
So when you said reduced space becomes M, C, and phi.
Right. So MC at the leading order, but then I treat the scalar field in perturbation theory on top of it.
Doesn't M get related to phi and pi phi?
No. It'll get related if I work at the quadratic order. It doesn't, because it's not there in the constraint, right? That's exactly what I was trying to tell you before. That just doesn't talk to the constraints or anything.
I think. But if you went to next order,
Then it'll.
It is G Newton times phi squared.
I suppose that it will get related. Yes.
You say M and C, right?
Mm-hmm.
Just go to the next slide.
Yes.
Now, okay, sorry for being maybe too dumb, but I would have thought that the Hamiltonian is conjugate to time translation.
Yeah. The correct.
You mean M and C specifically? I just meant some combination of
No, some combination. But
Yeah.
So sorry, maybe I'm being dumb. But in terms of phase space, why is C conjugate to M? Shouldn't you have?
What is C and what is M?
C was the size of the minimum.
No. M was
Okay,
the.
M was. Sorry, I meant C was the Hamiltonian, right?
Yeah.
Which was the
No. C is like basically this component of the extrinsic curvature tensor. It enters through the boundary condition, but because it's simple equations, the solution. It's all it's C everywhere. It becomes C everywhere.
Did you impose that it's asymptotically ADS?
Yes.
That is imposed.
Yes.
But then the asymptotic value of C is a global charge or something?
In maximal slicing gauge, when I show you the explicit BTC solution, this C becomes like some function of T bar, which is monotonic. So you can think of it as time directly.
As time.
As time.
So conjugate to H.
Conjugate to H or M. Yeah.
And where is the energy? Is it in M?
It's yeah. Yes.
Surely M is fixed, right? But it could be fixed by the BTZ mass, no?
It will get fixed to the mass. Yes.
Yes. No, I'm confused about you're saying M, C are independent of phi and pi. But isn't M? This is what you should not be allowed to choose the mass arbitrarily. Maybe you would get M equal to 0 or something. But why are you allowed to choose the mass arbitrarily at this order?
Because at this order, the scalar field is just a probe. It doesn't affect the
Correct, but
mass.
you can't set the mass arbitrarily. The mass of the asymptotic group.
Sorry, you should correct me, but
Mhm.
if you just look at classical solutions, you could have classical solutions where the scalar is not excited at all.
How much time do I have?
These are of a higher magnitude.
And
So this is just saying Hamiltonian is a moduli space of BTZs of different mass.
Yeah.
That's what it is.
Yeah.
So this M is just that flat.
That flat direction.
So if you fix the asymptotic value of the BTZ to be a particular M, then you will get M equal to 0. I mean, if you say the asymptotic mass of BTZ is fixed, then that
will fix this, yes.
So this M is just the fact that you have all these different solutions which range over different masses, where a scalar field is not existing.
Yes. Yeah, that's the statement. Okay, now I'll explicitly try to put the BTZ black hole in the maximal sizing gauge. So to do that, I begin with a metric of the following ansatz. So here T bar will be the maximal time. R is the areal radial coordinate. Phi is the angular coordinate, and these functions alpha, beta, na will be determined by solving Einstein's equation with this ansatz, together with the maximal sizing condition. And now the radial momentum constraint is straightforward. It just gives you this. So k phi just turns out to be a function of time, T bar. This is like that C I was telling you. The Hamiltonian constraint is also straightforward. You can solve this equation to get one of the functions, this metric coefficient, to get this. Now M comes out as another integration constant, which to begin with can be a function of time, but you can use another KRR equation of motion to show that it's actually independent of time, and this is what will become the mass of the BTZ black hole. An important point to note is that this function A actually diverges at the roots of this polynomial, basically when this object in the bracket becomes 0 at 2 places, which I call R plus and R minus. So what I'm trying to say is that this chart will eventually fail somewhere in the interior, and in fact it fails exactly at R equal to R plus. So I'll need two charts, one connected to the right boundary, another connected to the left boundary, and I'll have to match it smoothly at exactly the same point because they fail at the same point in the interior. So further you can solve the k equal to 0 equation, which I haven't showed you, to get the lapse with this standard boundary condition. So you have all the ingredients, you have all the metric components up to this function of T of T bar, which we have to figure out. Now to do that, we make contact with the BTZ black hole. So this is the standard metric of the BTZ black hole in any of the 4 wedges. So what you do is you write down the BTZ time t as a function of T bar and R, plug that in this metric and compare it with the metric I showed you, and the metric ansatz I showed you. That gives you these 2 equations. Now integrating the second, before that, this epsilon here is just a sign, and it's plus for the right chart, minus for the left chart. So you can integrate this equation to get this relation, and further you can take, so this relation, so what I'm trying to get is what this T of T bar is. And further you take R going to infinite limit, that gives you this equation. In the process, this equation could have told me what T of T bar is, but I don't, I have to first figure out what this T hat of F is. It's basically the BTZ time at R equal to R plus, somewhere in the interior, in the future wedge.
So it's something else, basically. In this 3-dimensional case, they also have boundary gravitons on top of the BTZ.
Yes.
Did you say it when I was up?
No, I didn't.
Those boundary gravitons?
So, yeah, right, the boundary gravitons are there, but they are large diffeomorphisms. So the way to include them is to generalize your boundary condition on the lapse and shift. And the algebra of those asymptotic values will have those.
Have you taken a boundary condition that kills them?
Yeah, but we can generalize it. That's what we are trying to do, thanks to Alok's comment, similar comments like you were saying. We didn't include it. So far our boundary conditions have not included that.
I see.
So if you say that lapse is only R by L, that doesn't include it. But if you allow for a function which depends on the angle, then it can. That's what our hope is. We haven't shown that. That's still being done.
I mean, the point is that these things which kind of just shift the boundary in some way, are what in higher dimensions would also give you fluid dynamics, right? I mean, so In 3D they won't have it, you just have these boundary gravitons.
Yeah, yeah.
But in higher dimensions, if I take the black hole
Hmm.
and I kind of boost it,
Yeah,
time dependently or something, then I'll get fluid dynamics.
I see.
Fluid dynamics.
So I will talk about one thing though. I'll talk about time translation on one boundaries
No, but
specifically.
a simple time translation just by the whole habit. Not in
I
the
see,
way that gives
I
you
see.
boundary graviton, right?
I see.
We're just talking about the
Exactly,
translating the time
exactly.
uniformly along.
Exactly. Yeah, yeah, yeah. That's right.
Where in the choice of gauge did you kill the large dip?
No. So you can actually take the equation for the lapse, which is like a Lagrange multiplier for different answers. And you can show that the solutions, what has been done. But if you want to talk about the whole Rasolo algebra of the boundary, that's possible actually. And we're just finishing it up. So that's all there, no problem. It's an important point.
Yeah. Okay, I'll proceed. So I was at this stage. No, I was here. Okay, so all the reason I'm trying to do all these things, which I now realize is not that important, is that I want to determine what this function t of t bar is, and that eventually gets determined when you try to match the left and right charts at r equal to r plus. So one point to note before I actually do the matching is that this this equation tells me that it's proportional to root a, so that also diverges at r equal to r plus, which implies that a constant t bar slice becomes tangent to a constant r hyperbola at r equal to r plus. So this happens for both the left and right chart. So now when I try to match the two charts at r equal to r plus, not only ensure continuity, I also ensure smoothness, at least the first derivative. And matching eventually gives me, determines everything. T of t bar gets determined through this equation. Not very important. Okay, finally, okay, it's good that I have two charts which cover this, but I would really like to have one single chart, one coordinate which runs through the entire spatial slice. So I introduce this coordinate x, which is defines in such a way that it's 0 exactly at r equal to r plus, where you join the two charts left and right. So the way this coordinate covers the entire thing is that x is 0 here. So x equal to 0 to infinity, it covers the right chart. From 0 to minus infinity, it covers the left chart. That's why it's a good coordinate which runs through the length of the wormhole slices. So I've just flashed the metric here. Finally, when you do this.
Sorry, I'm confused. At your ordered perturbation theory, were you sensitive to the back reaction of the scale or not at all?
No.
So this is this just the BTZ metric written in a particular coordinate system?
Yes, exactly. Because it's not sensitive, that's why I'm first considering just the BTC black hole, and then I'll put the scalar field.
Okay, so right now it's just exactly a BTZ metric.
Exactly.
In
a different form, such that the properties it satisfies certain properties that the constant time slices are maximal volume surfaces. Right, so some properties of these slicing. So the slices extend from the left to the right asymptotic boundary while smoothly cutting across the horizons. So here is a figure. So this is a Penrose diagram of the two-sided black hole. So these blue curves are basically different constant time slices, and as you can see, they smoothly go from the left to the right, cutting across the horizon smoothly. As t bar goes to infinity, the foliation settles to a final slice, avoiding regions near the singularity. And this is something that's actually useful for people doing numerical relativity. So as t bar goes to infinity, one approaches this final slice, shown in orange. And the region behind it and near the singularity is not covered by these set of slices. Okay. The lapse remains finite everywhere except at the final slice where the time evolution stops. Okay, this is just a coordinate transformation to the standard BTZ coordinates. An important point to note is that at the asymptotic boundaries, this time t bar of maximal slicing and the boundary time match exactly, which will be useful to us for when we do holography. All right. So here is another figure of 3D embedding of these wormhole slices. As time increases from left to right, they have this property that they stretch along the length and shrink along the circle direction. Now this second family of maximal slices, which lives completely inside the horizon, and they're a bit weird because they start from near the singularity and they move outwards, and as t bar goes to infinity for these set of slices, you approach the same orange curve I showed you in the previous slide. Because these slices never go to the boundary, it's not clear if and how they are useful for holography, and so this is the only one slide where I mention them. This one more thing I want to talk about is what happens when you do a time translation only on, let's say, one boundary but not on the other. So I've just drawn the figure. So these blue slices are the original slices of my wormhole constant time slices of my wormhole coordinates, and the green ones are their unique images under a right time translation, and they're unique because I fixed the maximal slicing gauge. So an interesting thing to note is that not only does this slice change in region 1, the right region, it changes in the interior as well as the other wedge. It changes everywhere except at the final left boundary, because you've imposed that as a, you've put it there.
So what are the blue lines here? The green then? What's the difference?
Right, so the blue ones are the original slices I showed you before.
Maximal slices.
Yeah, they are maximal slices. All of them are maximal slices.
So large diff moves blue to green.
Yeah, that,
So you have a diffusion which moves just one end.
yeah.
You can specify that and take the maximum volume. Just like
Exactly, because your fixed gauge, there's no choice in how what you have to do.
specify the two endpoints and then
Exactly, that's a point I was trying to emphasize. Okay, so
Just one. So this is the only large diffuse considered in this paper, because we are interested in just the propagation of the signal.
Yeah, so that's fine. If that's anyway a specific thing in 3 dimensions, in higher dimensions, these are the interesting large diffeomorphisms anyway. But yeah. In high dimensions, those other large diffs don't exist.
Yes.
okay, finally I'll come to the scalar field. So as I said, at quadratic ordinate perturbation theory, the scalar field is gauge invariant and physical degree of freedom after gauge fixing. So what we'd like to do is quantize scalar field along these maximal slices. But it turns out that the Klein-Gordon equation in wormhole coordinates is very hard to solve. And the reason for that is very simple, is that there is no time-like killing vector. So because of that, you cannot separate variables like you do in, for example, just the exterior. However, I must say that given, let's say, Cauchy data for the scalar field on, let's say, the t bar equal to 0 slice, there is no problem in solving this equation numerically because everything is smooth and well defined. So the strategy I'm going to involve is that I will basically what Suvrat mentioned some time back is that I know I can solve for the scalar field in the exteriors and analytically continue everywhere and get a solution everywhere. Once I have that, I pull that data back on maximal slices. So that's what I'm going to do now. So this is the solution in, let's say, the exterior region 1. One for me is the right wedge. Region 2 is what I call the left wedge. And this is the standard expression. So basically what you do is that you, now you have a time like killing vector, you separate your variables. So you have f, you can write as e to the minus I omega t times e to the minus I q phi times the function of r, which satisfies a hypergeometric equation which you can solve and get this mode expansion. That's all that's done here. Now the boundary operator dual to this is something you can get by taking the extrapolate dictionary. Is just this object where these A operators are the same. I mean, that's how you get it. So these A are the right boundary operators. Similarly, you have an expression for the scalar field in the left wedge in region 2. And I have added this tildes to differentiate with region 1. And the corresponding dual operator which you get by the extrapolate dictionary is this one. So once you have the solution in the exterior, you can either solve for the equations again in the future and the past wedge and match them at the horizons, or you can simply analytically continue the exterior solution a la Unruh to get the scalar field solution everywhere. So Unruh's basic point is that once you cross the horizon, you do it in such a way that the mode functions which have a branch point at u equal to 0 and v equal to 0 are analytic in the lower half u plane and lower half v plane. So that gives you 5 minutes. Okay, yeah, I think I'll be done. Yeah. So then you get these mode functions, the Hartle-Hawking mode functions, which are have support everywhere. So this, I just want to show that now you know the solution everywhere in all the 4 wedges. And this operators C are related to the left and right boundary operators by the standard Bogoliubov transformations. So it's good that we have a nice scalar field expression on the full space-time, but now I want to pull it back on these maximal slices, and there is a problem. The problem is, since our slices will cut across the horizon, the Hartle-Hawking modes are not well suited because their derivatives diverge at the horizon. So what I eventually want to do is write down the Hamiltonian for the maximal slicing.
There's another problem.
Yeah.
Which is, I mean, you can of course go to some different modes with just mode and so on.
Yeah.
But the problem has to do with how these fields transform under large disks.
Mm-hmm.
So you just take the left and the right modes
Mm-hmm.
and you just put them together. Then you fix the behavior under large diffeomorphisms. Because I know how that A omega that you wrote, that transforms in a specific way under large disks. You have no freedom.
Okay.
So where did your gauge condition go into the scalar field? Like if I've written down some other gauge,
Yeah.
then this scalar field would still have the same transformation, right? So where did the gauge condition go?
Yeah, I have 2 things to say to that. First is that I wish I could have solved or quantized the theory directly on my maximal slices, which I'm not able to do. The second is that this for me is more like an intermediate step to get to a final answer. What eventually I will get to is a Hamiltonian for this scalar field, which evolves along these maximal slices.
Did you get the scalar field right in the first place, and how would you get the Hamiltonian right? The question is that you're given the scalar field.
Yeah.
Let's forget about the coordinate transformation we'll do, but first you're given the scalar field at some coordinates.
Yeah.
Now, if you go back to the previous calculator, please, somewhere we had the oscillators. Could you go to the previous slide?
Huh.
Yeah. You see, those operators,
Yeah.
C's and so on, are fixed because they are related to boundary operators, these A's and A tilde daggers. They're the right and left operators. So now I fix the behavior under, let's say I do this e to the I hierarchy that you showed. Then the A's transform and the A tildes don't transform. So the scalar field transforms in a given way. Because I've told you how it transforms. But that's not related to my gauge. I wanted to transform in a gauge dependent way, right? Where did the gauge go?
Presumably his H
What?
omega q has some fall off at the boundary, right?
But that's given, no? That's the boundary.
By his choice of modes,
So,
right? Isn't here this simple statement that this is a complete set and he's just expanding the scalar field? into a complete set?
That is true.
That can't be wrong.
No, that can't be wrong. But now I just write, I transform it in a given way under large field. Then it's fixed, right? I've given you the scalar field everywhere, so this transformation is completely fixed. But I wanted the scalar field to evolve less in the bulk and more near the boundary. And so somewhere the gauge information should have gone in, but it didn't go in here.
So
This construction.
finally what I will, my aim here is to write down the scalar field Hamiltonian and interpret it as an operator in the CFTs.
Yeah.
So that operator will turn out to be completely gauge invariant. That I can tell you, but
No, it will
yeah.
definitely be gauge invariant by definition because everything is, even here everything is gauge invariant.
Mhm.
Because every A omega is a gauge invariant operator, it's the transform of a boundary.
Yes, yes.
So any expression you write will be gauge invariant. Let me say the problem another way.
Sure.
If you write those Unruh combinations, it will tell you that AR and AL have to have a particular 2-point function. Like A and A tilde.
Okay. Yeah.
Which is fixed by smoothness across the horizon.
Okay.
Now, if you do this e to the I HRT that we discussed in that state, as you just showed it's completely smooth in the bulk, right? It's a completely smooth transmission. But it will move the A's and it won't transform the A tildes.
No, it does, right? I mean, it does in the following way. If I understood what you're saying is that the reason it does it is because the slice changes everywhere.
That's the picture, but not in the expansion. That's what it should do.
Yeah,
but if you look at the expansion, A is a right operator, A tilde is a left operator.
Right.
So e to the IHRT doesn't talk to A tilde.
You've chosen the time to run the same way as a choice of gauge, basically.
No,
That's true.
The IHRT, by definition, commutes with A tilde.
He has not pulled his solution down to a maximum.
Right.
He has not yet done that. See, okay,
Yeah.
you all correct me. I think all he has done is, look, here's a complete set. I can write my scalar field and now I have a solution. Now I pull it back.
Exactly.
Show me the solution at all points in space. That's a unique operator. Now I can write it in any coordinate system I like. We can do the coordinate, but I've told you the scalar field at every point. So I've specified the operator. There's nothing more to specify. My feeling is that this will not satisfy the condition of acting the correct way in the e to the IHRT
I see.
large diff. And you can see it from here because the e to the IHRT commutes with A tilde, whereas it shouldn't. In your gauge, e to the IHRT should move fields in the left.
Yes.
Here in the expansion you've written, it doesn't. You don't have a choice. A tilde commutes with e to the IHRT. So it's not consistent with your picture, I think.
You cannot discuss
Okay.
the problem this way, Shiraz. I'm sorry.
I should have.
I'm so sorry. I saw Sandeep and then somehow. I think let him finish. Maybe.
Okay. I will discuss. Okay, so this is done. Right. So one problem I wanted to fix was that these mode functions are not smooth in the sense that their derivatives blow up at the horizon. So the horizon is at u equal to v equal to 0, which are crustal coordinates, null crustal coordinates, and it's not hard to see. You take a derivative, let's say, of this term with respect to u, it brings down a 1 upon u, which clearly diverges. Now to cure this divergence, we basically define a new set of mode functions. So we smear the Hartle-Hawking modes with Hermite functions in the frequency space. So this is my definition of new modes. Now these modes near the horizon, so by the way, this expression was close to the horizon. This expression again is close to the horizon, but of these modes, these new modes. And so now let's say you take derivative with respect to u, for example. It brings down this e to the curly theta, but this the Hermite function has an e to the minus theta square. So the integral is well defined and finite. So by going to this choice of mode functions, my scalar field has a smooth global expansion in terms of discrete mode functions. So this is the expansion. These E operators also annihilate the Hartle-Hawking modes because they are linear combination of the C's. So finally, I want to write down my scalar field Hamiltonian on the maximal slicing.
So in this final expression,
Yeah.
in your region 2,
Yeah.
did the scalar field have both left and right operators or only had left operators?
It has both.
Even in region 2?
Even in region
Only
2.
at the left.
Well, this is a complicated mixing in the frequency space. So in positions,
Usually in the Unruh thing that you do in Rindler,
Yeah,
that does
yeah.
not happen.
yeah.
And if you have just pulled back the operator you had to different coordinates, it will not happen.
These different coordinates. I think one of the main points here is that you can't fix any gauge you like.
You can fix any gauge. But
No, I'm sorry, you cannot. That's the whole point.
Oh, you cannot fix any gauge. Yeah, that's also true. You cannot fix.
I mean, the whole point is that there is a fortunate circumstance.
Correct. But here we are working in the quadratic approximation.
Yes.
So in that, the field on the left,
Yes.
I think it should be equal to the earlier field we got, right? Because we are pulling it back from one coordinate to another coordinate.
But I think maybe one of the details is that the background is not only in the maximal slicing gauge, but all the momentum constraints are also fixed. This is very important actually. So if you look at therefore the Klein-Gordon equation, with everything fixed, then you have no chance of making a gauge transformation or any coordinate transformation on the scalar. That's why it's gauge invariant.
No, it's gauge. Okay, we can discuss later, but maybe a chair is standing up.
This is my sorry.
Wait and say that please let him finish.
Sorry.
Okay, this. I'm on my final slide. So the final objective of all this is to write down the scalar field Hamiltonian, which evolves in this t bar time, which labels the maximal slices. Right. So it takes the following form. It's still quadratic because it's still free. However, it's not diagonal, as in it mixes different modes, and these kernels are actually pretty complicated. So here I've shown this kernel A, N prime, Q prime. So but it involves all the quantities that are smooth, finite, well-defined, right? The laps, the shift, the metric coefficients, the G mode functions and their derivatives. So dot represents derivative with respect to t bar. Prime is derivative with respect to x. And because everything is finite and smooth, you get a finite kernel and therefore a good operator. Hamiltonian as an operator is, you get a good Hamiltonian operator. This Hamiltonian is Hermitian by construction. It's completely gauge invariant operator in the product of two CFTs. And it describes time evolution of CFT states and operators in this time, and therefore it's the boundary description of infalling. So yeah, that's my slide.
We could discuss that. I think I already asked the question, which is, just to be clear on if you really had an expression for phi.
Yes.
And then you pulled it back from this coordinate system to a different coordinate system.
Yeah.
So then it would suggest on the left,
Right.
it only has the A tilde operators.
On the left, it has only A tilde operators.
You didn't just pull it back, you also did some smearing, right?
Yeah.
Okay, you also did some smearing.
Right. I define these new modes.
But if you want the field to be the same,
Just to understand, it's not the unroot. If I understand rightly, please correct me. You didn't just take the mode on the right and then through the unroot procedure get a complete mode
no,
everywhere.
I'm not saying that.
Okay.
But let me take the field at a given point on the left,
Mhm.
or at anywhere. Written in the old modes and the new modes, those fields are equal, right? This phi is just one operator. It's the same as the phi you wrote earlier. Phi is phi, no? So in particular, phi in region 2 has only A tilde.
A tilde is what? That's
A
the-
tilde,
A tilde is the left
A tilde
guy.
is the left operator.
Yeah.
So phi in region 2 is A tilde.
Yeah.
Good. Now let me add to d to the I HRT. That commutes with A tilde. So it does not move phi in region 2, which is inconsistent with the picture that you showed. Whereas you pointed out, the phi should move a little bit in A tilde. In region 2.
I think it moves, if you apply the full Hamiltonian that
No, I just want to apply e to the I HR.
what is the meaning of that?
It's a boundary gauge invariant operator. E to the I HR actually.
Yeah. But what is its continuation in the bulk? That's the issue.
You showed, no? It's the one that you showed which does the
That's
the graphs. Like if you show, could you show the graph, please? This is the continuation of this. This is e to the I HR. This operation I want to do. So now let me look at that point where the blue moves to the green, like the middle one.
Right.
And let me look at the field there
Right.
on the left edge.
Right.
So you can see that under e to the IHR, the field should go from the blue to the green, even though it's in region 2. It should transform.
Yes.
But the expression that you wrote is not
If you allow, see, what we have done is we have fixed an additional gauge in the sense that we have identified the clocks on the two sides.
No, e to the IHR, I can still act. It's an operator in the theory. I can act with only e to the IHR. I don't have to act with e to the IHR plus
No,
HR.
I think there is a problem in that issue. There is an issue there in what you're saying.
Boys,
We
can I
discuss
suggest
this.
you continue discussing over coffee?
Okay, fine. Yeah. You encourage me to answer.
Okay.
Just